Hello all, welcome to this course on time series modeling and forecasting using R. Alright. Now again, until the last lecture, especially in this week, we focused more on, let's say, model identification, then model estimation using MLE, method of movements, OLS, etc. And towards the end of a few lectures this week, probably last lecture and the one before that, we focused more on diagnostic checking. Alright. So here in this lecture, we'll focus more on a practical example. So this entire lecture would be, we'll do some simulation based ideas or simulation based exercises in R. Okay. Now again, if you vaguely remember from the last R code that we had in the last week, which was code 3. So basically today we'll start with code 4 as you see here, right? And then from the last week's R code, we focused on a bank data, right? So again, just to be in line with what is happening with that data, we'll again work with the bank data. Let's say when it goes to diagnostic checking or probably modeling something and so on and so forth. Okay. Alright, so let's start. So before that, again, we have to import a couple of packages. So let's say T series and then forecast. Okay. Now again, I'm just repeating this again and again, that if the packages are not already there in the R environment, you have to go to tools and then basically install those packages. Alright. So let's say click on install package, then you type in the name here, let's say T series or forecast or whatever other package you want to install, and then again make sure that this is from this drop down menu, it's clicked on repository. Okay, it's clicked on repository and then click install. Okay, and once you've installed, then again make sure that you call the packages in the R environment using library command. Okay, so we'll do that now. So library T series and then library forecast. Okay. And again, this is the console window. So whenever you are kind of bringing any package in the R environment, and if you don't have any errors, it will basically give you this sign like that. Okay. For example, here when you outputted library forecast, it did not give me any error, and then R sort of successfully brought in the forecast package. Okay. All right. Now before we go about dealing with diagnostic checking, we'll do a very simple exercise, which is simulating from a Gaussian white noise process. Okay, so simulating some set of data or set of observations or set of time series values from a Gaussian white noise process. Now again, what do you mean by Gaussian? So probably from one of the earlier lectures, you must remember that Gaussian means nothing but a normal distribution. Okay, so other name for a normal distribution is Gaussian distribution. Okay, and again, white noise probably all of you must know by this time, right? So white noise is nothing but a collection of random movements which resembles a noise, and probably you can assume a zero mean and some fixed variance. Okay. All right. Now again, how do you simulate from a Gaussian white noise, which is nothing but normal white noise? So in R, you have this R norm function to generate some values from a normal distribution. Okay. So how many values are you generating? So let's say if you delete this 0 here, and then initially we'll start with, let's say, just 10. Okay. So the first argument or the first entry in this R norm function is how many values you want to generate. For example, as you can see here, so n or the sample size, then you basically specify mean and the standard deviation. Okay. So here say we are assuming that the mean is 0 and then the standard deviation is simply 1. So this is more like a standard normal or a standard Gaussian variable. Okay. All right. So let's run this. Okay, and then we are giving it a name which is x basically. So again, if you want to find out that what exactly is the data that you have generated, you can click on X and then hit enter. So pretty much all these are the normal variables where mean is 0 and variance or the standard deviation happens to be 1. Okay. And of course, if you keep on repeating this number of times, at every entry or every iteration, you should get different values because you are performing a simulation based exercise. Okay. So again, what I mean by this is that if you again run this, let's say the same code R norm, and then again get hold of what my x is, then you should get different values, of course, right. So since you are simulating, at every iteration it should hopefully give you a slightly different kind of a set of observations. Okay. All right. So again, remember that we are kind of generating some normal variables with mean 0 and variance 1, and then we are kind of giving that vector name as x. Okay. Now the next thing is to produce some plots. So let's see, the first is we'll draw a histogram. Okay, and then let me zoom in on the histogram. All right. So this is exactly how the histogram looks like. Now again, just by looking at the histogram, and then assuming that you have generated the sample from a normal distribution, this is nowhere close to a normal, right? Because again remember that if the distribution has to be normal, the histogram should be kind of symmetric, right? So there should be higher bars in the middle and then lower bars in the both the ends, but this is more like a skewed kind of a distribution. So essentially this is left skewed, right? Because you have a long tail on the left side. Now again, why is this happening probably? So even though you simulated from a normal distribution, but why isn't the histogram looking kind of a symmetric in nature? So again, the answer to that question is that your sample size is very, very small, isn't it? So you're only generating a handful of normal distributed values. So again, if you're only generating 10 such values, so obviously from 10 values you won't get a completely symmetric kind of a density curve, okay? And again at the same time, so if you try to plot the data, let's say blindly, so plot x and then type equals L. So type equals L means that you want a line plot, you want to join all the dots there, okay? So let's see what it gives you. So this is the plot. Now let me add two lines here. So the first line is I'm adding a horizontal line at the mean of the generated data, okay? So h equals mean of x. So whatever the mean of the data is, so it will only produce a horizontal line at that value. So this is my first horizontal line, and then I'll add another horizontal line in a different color, let's say blue, at 0, okay? So essentially I'm adding two horizontal lines. The first one is at the mean and then second one is at 0, right? And this is just to tell you that again if I zoom this plot slightly, then we'll see that what is going on. So you can actually see small difference between the red line and the blue line. Can you see that? So the red line and the blue line are not superimposed exactly, right? So the actual mean of the data happens to be slightly more than 0, okay? And again this may not be a very good indication. So probably what we'll do is we'll again let's say simulate and then see what happens. So let's say again if you simulate the same thing and again I try to plot it, and hopefully we should get slightly more of a difference this time. So let's say, yeah, so red line is here and then blue line is there. So now probably this plot is making more sense as to what may be a problem. So again, so I'm again simulating a slightly newer data set now. So again all these observations are again still coming from a normal distribution with mean 0, by the way. So this blue line is at 0 and this red line is at the mean. And then here you can clearly see a large difference between the actual mean and 0. So 0 is the assumed mean, right? So since you are generating the observations from a normal distribution with mean 0, you should expect that the mean of the data should also be very close to 0, which is not happening here. So you can see a large difference here. And again it boils down to the same question as to why this is happening. So both these things are happening because your sample size is small, okay? So what we'll do is we'll again, so it says here also, so repeat the above code with a larger n. So now what we'll do is we'll probably increase this to let's say 1000 and then see what goes on, okay? So again generate the normal observations, but this time 1000 in number. Again we're still assuming mean is 0, variance is 1, and then we'll see how the histogram looks like. So if you look at the new histogram, then now you can clearly see that you can sense a symmetric kind of a resemblance. So the density is kind of looking more like a symmetric in nature, which is exactly what we want, all right? Okay, and then how about the plot now? So let's say if you plot the observations, so this is the plot along with the mean line which is in red and along with the 0 line which is in blue. And if you zoom this plot now, then so here you can't even make out the difference between the red line and the blue line. So they are so close, which means that the mean of the data is so close to 0, which is again what we expect, okay, that you can't even differentiate between the two colors, okay. So essentially this is exactly what we want to achieve, right? So if you are taking let's say a slightly larger sample which is 1000, then obviously the generated sample has to resemble a normal distribution exactly, okay, both in terms of let's say histogram and in terms of let's say measuring the mean of the data, etc. All right. So I think this is a small initial part in this code, and then now we'll pay attention to diagnostic checking. So we'll basically try to combine all that we've studied in the last lecture and the one prior to that, and so on and so forth. And again we'll take up the same data set that we worked upon in code 3, okay. Now just to give you a brief, summary of what that data set was. So we are basically focusing on this monthly volume of commercial bank real estate loans in billions of dollars. Okay. So you have a particular data set called as bank case, and then this data set is stored in a text file. So firstly, how do you bring it? So you have multiple ways firstly, but as.ts again, so as.ts ensures that you are bringing the data as a time series structure. Okay. And on top of that, the scan function is basically bringing the data in the R environment. All right. So and then we are giving it a name as bank underscore case. All right. So let's run the data. So bank underscore case, and again, if you want to find out that what are the observations underlying the data, you can actually print the name of the data. So bank underscore case, and you can actually see the entire data set being printed in the console. Right. So each of these numbers actually gives you monthly volume of commercial bank real estate loans in billions of dollars. Okay. All right. Now again, vaguely, if you remember what we covered in code 3 pertaining to the same data, we are trying to fit some ARIMA model, if you remember. All right. Now the first thing that we did there is that the actual data is not stationary, if you remember that, right? And then it contains some trend. So if the original data has some trend, what do? So you difference the data, right? So you apply the differencing operator. Okay. And essentially, how many times did you want to difference the data? Even if you again go back to code 3 and then probably run that again or something like that, then you can actually remember that we were supposed to difference the data twice. Okay. So again, probably I'll show you again as to why that was the case. So let's say if you difference the data once and then run this line, and then probably you run this ADF test. So ADF is augmented Dickey-Fuller, right, which is used to test for stationarity. So if you run this ADF test on the first difference, then what do you get? So you get that the p value is larger than alpha. So if the p value is larger than alpha, we fail to reject the null, right. So if you fail to reject the null, we have to go with the null hypothesis, and for any ADF test, the null hypothesis is that the model is not stationary. Okay. So which kind of concludes that the first difference is not stationary still. So how do you handle such a situation? You go for the second difference. Okay. So you create the second difference, which is nothing but difference of the first difference. So something like that. And again, if you implement this ADF test on the second difference now, it should tell you a story which is slightly different. So now the p value is less than alpha, which is exactly what we want. So if the p value is less than alpha, we should be able to reject the null. And if you are able to reject the null, we have to go with the alternative. An alternative hypothesis is that the model is stationary. Okay. So this is just a summary kind of a idea as to what happened in code 3, right, if you don't remember vaguely, right. So we had to difference the data twice basically, and then if you remember that we fitted this ARIMA model with these orders, so 0, 2, 1. Okay. And then again, you have to fit this ARIMA model on which data? So you have to fit this ARIMA model on the actual data, which is bank underscore case, and not on the difference data. And why is that? Because you're keeping this middle order to be 2, right. So any ARIMA model where the middle order is 2 is telling you that you have to actually difference the data twice to achieve stationarity. Okay. But if you're fitting an ARIMA model where the middle order is 2, that model has to be fitted on the actual data, isn't it? So your actual data follows an ARIMA model with these orders. So 0, 2, 1. Okay. Now again, one small point, just a summary kind of a point, that why exactly these orders and not some other orders, right? So I'll show you exactly why, and I think we discussed this point in the earlier code also, that once you fit this ARIMA, you kind of get hold of the fitted coefficients and so on and so forth. So here you see that, so 0 to 1 essentially is nothing but ME1. Right. So you don't have any AR component. So this kind of gives you the MA coefficient, and here if you see, it produces an AIC value. So I think until last time we were not confident about the AIC as to what it means, right, but now we are. So AIC is Akaike's information criteria. Okay. So just try to remember this value. So AIC value is 26.1. Okay. Now what we'll do is I'll change the order slightly and then see what happens. So let me change this to probably something like 1, 2, 1. Now again, remember that if you are changing the orders have to be in close neighborhoods of the current order. So suddenly you can't change the order to 10, or 20, something like that. Okay. So, if the expected ordering is 0 to 1 and if you want to make some changes and see if your model fit is improving or not, then you have to actually change the orders in close neighborhoods. So, something like 1 to 1. Okay. So, now we will see what happens. So, if you try to fit this model, this ARIMA structure, and then again get hold of the fitted coefficients and so on. But then now by the way, remember that this is not a isolated MA structure. So, you have an AR component as well as a MA component. Okay. So, there should be both the coefficients that the model should give you, right. But now the thing is that the AIC value has increased now. So, earlier it was 26.1, right, if I am not wrong, but now the current AIC value is slightly more, which is 27.9. Okay. So, ideally speaking, if you remember what the goal should be, so goal should be always to minimize the AIC as much as possible. Okay. And hence you may try this out and then you may play around with the orders if you want. So, play around means that change the AR order and MA order very slightly and then see what AIC you are getting. Okay. So, it so turns out that for this particular triplet, so 0 to 1, the AIC is in fact the least. Okay. So, hence we will go forward with this ARIMA structure. So, 0, 2, 1. So, let me refit this again. Okay. And then this is the fit. So, AIC is 26.1. So, now once you fitted the model, we can actually get hold of the residuals using a dollar sign. So, let me show you exactly how. So, if you delete this for a second and if you only have fit, right, and then if you apply a dollar sign afterwards. So, can you see that one can actually select out of all these options. So, if you want to get hold of the coefficients or if you want to get hold of the variance or let us say the log likelihood or the AIC, and then here if you come down the line you have a residuals option, right. So, if you want to get hold of all the residuals of the fitted model, you basically select this and then run this code. Okay. So, now and then I am storing all the residual data in the RES name. Okay. So, RES contains all the residuals for the above fitted ARIMA model. Okay. Now, we will do some checks. So, we will see a initial plot of the residuals. So, again type equals L would give you a line plot. So, this is exactly how the residual plot looks like. So, let me zoom in slightly. Now, again just by looking at this plot we are not seeing any major problems as such, right. So, one can actually assume that the residuals are in fact behaving as if a stationary series behaves, right. And again you do not see any major changing variance problems also, right. So, because pretty much all the residual fluctuations are within some tight variance bands. Okay. So, for example, you are not seeing any fanning out or funneling in kind of a structure here. Okay. Alright. So, in a way the residual plot is kind of not looking bad at all. Okay. Now, what we can do is we can again draw a horizontal line at 0 if you want. Alright. So, let me run this and then show you the plot again. So, let us say this is a complete plot, right, where you see the behavior of the residuals along with the 0 line. So, here again if you see, you can pretty much see some random movement along the 0 line, which is exactly what we want in terms of the residuals. Okay. And now we have come to a point that we will do all the checks now. So, firstly normality check. So, are my residuals indeed normal or not? So, for that we will create a histogram. So, let me run the histogram, and if you zoom in on the histogram you can actually see that the residuals may be symmetric, right. I mean there might be a slight skew here probably, but otherwise you do not see any major problems when it comes to the histogram. Okay. But we indeed will not only rely on the histogram. So, we can get hold of Shapiro-Wilk test. So, in R you have a very simple command called as Shapiro.test, and then that you apply on the corresponding variable. So, in this case it is RES, which is residuals. Okay. So, we will see what happens if you apply the Shapiro test, and then here you are getting a p value which is 0.2337, which is bigger than alpha. Okay. So, anytime if we get a p value bigger than alpha, we fail to reject the null, and then for Shapiro-Wilk the null hypothesis is that the distribution is normal. Okay. So, here we can actually safely conclude that the distribution is indeed normal, and for that matter we can also test using Jark-Bera test. So, again in R you have this function Jark.Bera.test. Okay. And again you can see that the p value is indeed bigger than alpha. So, both Shapiro test and Jark-Bera are giving the same conclusion that the distribution of the residuals might be normal. Okay. And now the last thing one can do is one create this normal QQ plot. So if you create this normal QQ plot along with the straight line, so let me zoom in on the QQ plot. So here you can see that pretty much all the observations, probably apart from these three, are kind of falling on the line, right, which is exactly what we want. Okay. So in fact, histogram, Shapiro test, Jark-Bera test and the QQ plot are kind of concluding the same thing. Okay. Now just in case I will show you that if the distribution is not normal, then how does the QQ plot look like? Okay. So for that what we will do is we will create some simulated data from a chi-square distribution. So R chi-square is to generate some simulated values from a chi-square distribution indeed, and chi-square is not normal, right, with these parameters. So 4 is the degrees of freedom for the chi-square, and then how many values we are generating? We are generating 100 values. Okay. So let me run this and then again show you the QQ plot of the chi-square sample, okay, along with the straight line. So here can you spot the difference now? So if you zoom in, so of course we can. So at both the ends you have lot of departures from the straight line, which is not what we want, right. So if you are observing something like this in a normal QQ plot, then you can actually safely conclude that the distribution is not normal, which is the case here, right, because we are simulating the data from a chi-square distribution. Okay. Alright, so once you establish normality, then what is the next thing? So detecting serial autocorrelation. So or in other words, detecting whether the residuals are independent or dependent. Okay. And then for that we have covered these two very famous tests, so Box and Pierce and then lung box. Okay. And again here you have to specify a couple of things. So to specify the lag, so let us say up to how many lags you want to check, right. So in this case I have to check for up to the 10th lag, something like that. Okay. And in both the situations you have a common function in R called as box.test, alright. And how do you ensure that you are actually testing using a box Pierce or lung and box is that you specify that in this type. So type equal to either box Pierce or lung box. So both box Pierce and lung box are inbuilt kind of choices when it comes to type. Okay. Alright, and then both these tests have to be again applied on the residual, right. So RES. So we will see what this gives you. So if you run the box Pierce test, p value is 0.6278, and if you run the lung box test, the p value is again 0.5188. So in both the situations the p value is very large than 5% or alpha, right, and again the same conclusion. So here again we can conclude that we fail to reject the null, right, since p value is larger than alpha, and whenever if you are failing to reject the null, we can actually conclude that there is no serial autocorrelation in the fitted model or among the residuals. Okay. So in fact using both the box Pierce test as well as lung and box test, you can actually conclude that there is no serial autocorrelation among the residuals. Okay. Okay, so now once we are done with checking for normality and serial autocorrelation, now the last thing is to check for heteroscedasticity or changing variance, alright. And then for that, as we have covered in the last lecture itself, we have all these possible choices. So one can actually look for creating some ACF plots and PACF plots of the residuals themselves. So okay, so we will see that what these two plots kind of tell you. So if you create this ACF plot and the PACF plot, so let me zoom in on the ACF plot first. Okay. Alright, so again this is the ACF plot of the residual data and not the squared residuals as of now, right. But again here you can see that apart from the first lag, which is nothing but 0, all the further correlations are inside the bounds, which means that residuals themselves are behaving as if a stationary series behaves. Okay. So again this is exactly what we expect, or this is exactly what we want. And possibly the same thing should be seen in the PACF also. So if you create the PACF plot and then zoom on the PACF plot instead, then again the same story. So in fact PACF is better, right, because all the correlations regardless of whatever lag they are at are not significant, because all these spikes are in between the confidence limits. Okay. So again both the ACF plot and the PACF plots are suggesting that the serial autocorrelation or heteroscedastic nature of the residuals is kind of maintained. So residuals are behaving as if they are a stationary kind of a series. Okay. But like we discussed, we have to also check for ACF and PACF plots of the squared residuals instead, right. So, and then not just the actual residuals. So, what do we see here? So, let us say if you create this ACF plot of the squared residuals instead. So, we will see how the plot looks like. Okay. So, this is exactly the ACF plot of the squared residuals. Let me zoom in on the ACF plot, and again we see the same kind of a story. So, apart from the lag 0, all the further correlations are between the bands, which means that the correlations are not significant. Okay. And then lastly, how about the PACF plot of the squared residual? So, again it should resemble a same conclusion. So, again if you draw the PACF plot of the squared residuals, then again you can see a same structure, right. So, again all the correlations or all the spikes, regardless of what lags they are at, are kind of not significant, because all these spikes are between the confidence limits. Okay. So, in a way this is more of a visual check. So, one can actually create some ACF plots or PACF plots of the residuals themselves, or on the other hand one can create some ACF plots and PACF plots of the squared residuals in a way. Okay. And now rather than creating ACF and PACF plots of the residuals or the squared residuals, so why not just formally test this, right, using a formal hypothesis test. And here we kind of apply the White's test, right. So, if you apply the White's test, so again in R you have a simple looking function called as White dot test. So, if you apply this White dot test on the residual data, then what do you get? Okay. So, if you apply this White dot test on the residual data, right. So, the p value is again very large. So, 0.8992. So, again the same conclusion that was drawn from the earlier tests also, that if the p value is bigger than alpha, you fail to reject the null, and the null hypothesis under either White's test or Bruce-Pagan test that we covered in the last lecture is that the variance is constant. Okay. So, here since the p value is bigger than alpha, it is 0.89, close to 0.9, which is very large, then we fail to reject the null. So, we can actually safely conclude that the variance is not changing or the variance is constant. Okay. So, this is pretty much checking for normality, checking for independence, and then checking for changing variance for the residuals. Okay. And I just like to point this last comment here, that in R you have this very interesting function called as check residuals. So, what you do is you kind of apply this function on the fit itself, right. So, if you remember, bank underscore fit is my ARIMA fit of the model, right. So, if you apply this check residuals function on bank underscore fit, what does that tell you? It sort of gives you all these plots in a bunch, right. So, initially you can see that this is the behavior of the residuals, probably this is exactly what we saw just a short while back, right. So, this is nothing but a plot of the residuals, it says here, right. So, residuals from this fitted ARIMA model of these orders, so 0 to 1, and then here you see the ACF of the residuals, okay, and here this is a check for normality. So, in a way this check residual item or check residual function in R is an inbuilt function. It sort of gives you all possible angles. So, let us say checking for independence through this plot, or probably checking for normality through this plot, or probably checking for constant variance through this plot, because even if you simply have a plot of the residuals, here you can clearly observe that the variance is not changing, right. So, I will say that one suggestion is that once you are through individually with all the above sections, for example, normality or serial autocorrelation or changing variance, right, then just to back it off you can actually use this check residuals functions in R. Okay. So, I think in today's lecture we have managed to cover quite a lot in terms of diagnostic checking from a practical point of view, right. Now, again let us say tomorrow if you want to analyze any other practical data set, the only thing you have to do is you have to change the data right here. So, instead of bank case you can actually bring in some new data that you want. Okay. But again remember one thing, that you should not jump to diagnostic checking directly, right. It is always a process. So, you first try to fit some model. So, here we try to fit this ARIMA model, right, because once you fit a model then only you get access to residuals. Without fitting, how can you check for diagnostic checking, right. So, you have to fit a certain model which is the best possible model given all different, let us say, information criteria or probably visual checks and so on and so forth, and then once you come to a concluding kind of a model structure, let's say ARIMA with certain orders, then one can actually get hold of the residuals of the model and then perform all these diagnostic checking, let's say either individually or using this check residuals function in R. Okay. Thank you.